Hi, I am Mariana, a biomedical engineering master's student in University of São Paulo, and I represent my work, Regression Approach for Cranioplasty Modeling. Bone reconstruction of cranial areas is a challenge because of complex anatomical shapes, unique characteristics of each bone defect, the presence of vital adjacent anatomical structures, and the high risk of infection to which the patient is subjected. The goal is to statically restore the affected area and rehabilitate its function, restoring patient self-esteem and normalizing his or her social life. The state-of-art of patient-specific implants is the use of a 3D model based on the reconstruction of the bone structure of the patient's skull from computed tomography images. The missing bone segment is virtually modeled based on the patient's own anatomical information with the ideal geometry. Then the implant is fabricated via subtractive or additive manufacturing. Using patient-specific implants brings significant advantages for patients and medical professionals in reducing surgery time, persistence adaptation trauma, patient recovery time, and increasing surgery and implant success rates. The use of commercial and user-dependent software makes the production process of such implants more expensive and affects its standardization and repeatability. Semi-automatic and automatic methodologies were developed for automating the critical steps of the modeling process. The cited studies on my paper use information from the morphologically healthy contralateral skull hemisphere to generate the segment corresponding to the bone defect. The present work proposes a 2D investigation of which dataset results in the closest polynomial regression to a gold standard structure, combining points of the bone defect region and points of the healthy contralateral hemisphere. Such dataset analysis is not addressed in the cited reference studies and can improve semi-automatic and automatic methodologies results. For this study, 5 computed tomography skull image series were obtained from 2 databases, where the images in DICOM format were unidentified and anonymized prior to making them available to the public domain. The methodology consists of Python scripts. The first step of the methodology is the use of a fixed threshold value of 200 Hounsfield units to determine the interface points between bone and adjacent tissues. Each bone contour is defined as a list of points with X and Y coordinates in pixels for each image. Those are the gold standard contour points and represent the external bone surface of the skull. In order to obtain the phantoms, images above the orbit region and below the skull apex are selected from the image series of the 5 patients listed in Table 1. Ellipsoids with different parameters are used to generate small, medium, and large bone defects. So 3 phantoms are produced for each patient, resulting in 15 phantoms. In this figure, we have 4 phantoms, and the blue dots are the phantom contour points. In order to use the information from the contralateral skull hemisphere, it is necessary to align it with the bone defect region. Considering that the skull is approximately symmetric, a mirroring operation is convenient. It is necessary to define a contour symmetry axis to perform this operation, so it is defined per image by a horizontal vector and a reference point calculated as the mean between the maximum and minimum values of the X and Y coordinates of the gold standard contour points. Then the mirroring operation is performed on the phantom contour points. The figure shows the overlap of phantom contours in blue and the respective mirrored contours in green in different skull regions for 2 patients. Good visual overlap of the contours can be observed in all phantoms, despite the anatomical differences between them, indicating convenient positioning of the data for the tests. Since we have only lateral bone defects, we perform the next steps only with the points in the hemisphere of interest. This aims to increase the computational efficiency of the methodology. The set of reference points included in the regression affects the morphology of the resulting curve. Therefore, it's important to define reasonable criteria for the region that provides such reference points. First, we set the initial and ending point of the bone defect by finding the largest interval between the X coordinates of subsequent points, which are the more central X's on the figure. Then the initial and ending point of the evaluation region are set using a 10 mm Euclidean distance from these bone defect points, resulting in the more external X's on the figure. The objective of the present study is to verify which dataset, by combining phantom counterpoints and mirrored counterpoints, improves similarity measures between the gold standard counter and an estimated counter. This estimated counter is a polynomial obtained by a fourth-degree two-dimensional polynomial regression using the referred dataset. The chosen similarity measures are root mean square error, that are called error for short, and Hausdorff distance. Tests A through D are performed for each bone counter comprising the phantom bone defect using different datasets as input points to the polynomial fit calculation, combining phantom counterpoints and its mirrored points once or twice. The use of the same dataset twice aims to influence more strongly the curvature of the resulting curve. The bone defect starting and ending points delimit the region for calculating the similarity measures. The evaluation region is not appropriate because this set of points comprise the bone defect edges, which are present in the gold standard and therefore in the phantom identically. This would artificially reduce the error between the two datasets. The graphical results obtained from the tests indicate that the polynomial regression is satisfactorily filling the defect with the desired shape. On the left, the gold standard counterpoints are in blue, mirrored counterpoints are in green, and estimated counterpoints are in red. The image on the right shows the phantom bone counter in blue and estimated counterpoints in red for all the 4 tests performed here for one image of one patient. The mean similarity measures were calculated between the gold standard counter and the estimated counter in the bone defect region, considering all counters that comprise the bone defect of each phantom for each test. Table 2 presents the numbers of counters considered in the calculation of similarity measures for each phantom, which vary based on the patient's anatomies and image series and size of the defect. The similarity measures varied considerably between patients and between defect sizes in the same patient due to anatomical variations. They increase as the size of the defect increases, as expected, because the curvature of the phantom contour becomes sharper and potentially more complex, not necessarily corresponding to the characteristic curvature resulting from the fourth-degree polynomial regression. In these cases, the mean error and Hausdorff distance are decreased by using the mirrored contour, which provides this curvature information. This fact is demonstrated by the increase of error for test A, which only uses information from the edges of bone defect in the regression, in relation to the other tests as bone defect size increases. Considering only tests B, C, and D, in which mirrored bone contour information is used in the regression, the mean error in test C is the lowest in 4 and 5 patients with small defect and all 5 patients with medium and large defect. The cited proportions are identical regarding the Hausdorff distance. Here we present the mean Hausdorff distance, which has the same profile as the mean error showed before. From the results, the following null hypothesis is formulated. There is no statistically significant difference between the error or Hausdorff distance obtained for test A and for each other test, B, C, or D, considering all the phantoms. Since the datasets are paired, it's verified and confirmed that the datasets resulting from the difference between the pairs for both similarity measures have approximately normal distributions. That condition allows the calculation of p-values using the t-test. The null hypothesis is rejected for all test pairs regarding the error values and for test pairs AB and AC regarding the Hausdorff distance, indicating that there is significant difference between these test results. Combining the statistical test results and the observations made from the mean error and mean Hausdorff distance, we conclude that the dataset formed by the phantom counterpoints twice and the mirrored counterpoints, which was test C, is the one that significantly improves the similarity measures. This dataset will be used for further development and testing of a 3D polynomial regression approach for semi-automatic generation of a cranioplasty polygonal mesh. Thank you.